with NOAA's National Water Center, Programmatic Update and Opportunities for Collaboration. This webinar series has been convened by NOAA's National Water Center to invite current and future collaborators to discuss current initiatives and opportunities for engagement. This town hall will contain a 1-hour presentation, give or take, followed by a Q&A portion. My name is Julia Masterman. I'm the Education Outreach Specialist for QUASI. QUASI is the Consortium of Universities for the Advancement of Hydrologic Science, and our mission is to support water science and advance water science by strengthening interdisciplinary collaboration, providing critical infrastructure, and through our data services, and promoting education in the water sciences at all levels. QUASI also assists in the coordination of the National Water Center Innovators Program Summer Institute, and we are thankful for the National Water Center team for joining us today. Before we get started, a few logistical things. Firstly, this webinar is being recorded and will be posted on the QUASI YouTube channel later this afternoon. Secondly, we ask that you use the Q&A functionality to submit questions to our speakers during that Q&A portion at the end. And finally, we expect that all involved with QUASI Cyber seminars promote and maintain a professional, considerate, and respectful collaborative virtual environment. Thank you again to all of our speakers and at the National Water Center and beyond for putting together this opportunity for engagement. And with that, I'll pass the mic on to our hosts. Thank you.
Thanks very much, Julia. Good afternoon, everybody. My name is, or good morning, depending upon where you are. My name is Tom Graziano. I'm the Director of the Office of Water Prediction, and I will just be one of many speakers from the Office of Water Prediction and National Water Center with you this afternoon. A few opening remarks before I hand it over to our Chief Scientist in the Office of Water Prediction, and Fred Ogden. So first of all, I think as many of you know, we are in the midst of a transformation, if you will, with regard to water prediction. Historically, in our agency, we have provided forecasts at roughly 3,600 USGS stream gauges across the country on a daily or more frequent basis. And based upon stakeholder interactions over the course of the past decade or more, what we've learned from our stakeholders is, while they're pleased to a large degree and with regard to the services we're providing, new enhanced information is needed to inform the many decisions that they make that keep them up at night. And it's information related to flooding, with drought, water availability, water quality, and then the impacts of climate change. They're looking for information that's of higher fidelity, both in space and time, than we have historically provided. And they're looking for us to work with them to link that information to other geospatial information to inform the critical decisions they make across all sectors. So toward this end, and as a complement to the forecasts that are made routinely at our 13 river forecast centers across the country, I think many of you are familiar with our efforts to develop and deploy the first ever continental scale, high resolution operational water model operating on our weather and climate operational supercomputing system, or the National Water Model. We implemented that first in August of 2016. Since that time, we have implemented 4 upgrades to the model, the most recent of which was on April 20th of this year with version 2.1 of the National Water Model, which included a domain expansion to the full Laurentian Basin, Puerto Rico, U.S. Virgin Islands. On the doorstep here is that we're working on now and working collaboratively with the National Center, folks from the National Center of Atmospheric Research, or NCAR, as well as the QUASI and the broader community. And we're developing, as well as our sister agency, the National Ocean Service. We're working on version 3.0 of the National Water Model for deployment next year. It will be the first time that we will actually be linking in real time operationally freshwater forecasts generated by the National Water Model with coastal predictions, wave, tide, surge predictions made by the National Ocean Service's STOS, or Surge and Tide Operational Forecast System. for all coasts of the United States. So we are pretty excited about that. And so that is another step along this pathway. However, what we have heard from all of you in the broader community, largely via the vehicle we know as the Community Advisory Committee for the Office of Water Prediction, or CACWP, through the various meetings that we've had, the recommendations born from that meeting, there has been one consistent, I will say loud, clear message from all of you, and that is that this is we should be open source. This should be a true community development, and we should be looking for ways or opportunities or employing a framework which enables all of us to work together, develop capabilities within a common framework, using common APIs and interfaces to leverage different investments across the enterprise to run model configurations that support each of our respective needs. So toward that end, we have begun work to develop what we're calling the next generation National Water Model Framework. And what you will see demonstrated today by our team is that framework in an operating fashion. We are really excited about this. We think that this is a first step among many to be had collaboratively with all of you. The requirements we used to establish this first or initial foray with this framework was based upon meetings with our federal partners and others, and followed by technical meetings with those same federal partners and others to craft this first working version of this framework. So with that, as an introduction, I'd now like to hand it over to Dr. Fred Ogden, our chief scientist, as I mentioned, and he's going to take you through this afternoon's session. So good afternoon. Good to see you all again. Really excited about working with you, hopefully in the future on all of this. Fred?
Hey, thanks, Tom. Can everyone hear me okay? Testing?
Yeah, got you, Fred.
Okay, great. Thanks. So we have a number of people that are going to talk today, several from OWP and Chris Massey from the U.S. Army Corps of Engineers. I'll go ahead and get started. Let's go to the next slide, please. So I want to talk about the philosophy of the design of the next generation water resources modeling framework. The next generation national water model will be a particular configuration of this framework, but the framework is really intended to be broader than just that. Next slide, please. The National Water Model, many of you might remember, it was proposed originally in 2011 by Quasi as a community model. There was a lot of interest in the academic and research communities, but ultimately that effort lacked agency support. In 2014, the National Weather Service recognized the potential for predictions outside of the traditional 3,000 some forecast points that the river forecast centers make forecasts at. And in 2016, National Water Model version 1.0 was operationalized by National Weather Service, and it was based on WRF Hydro, which is NOAA MP for the land surface schemes with added routing functionality plus a conceptual groundwater component. In 2021, National Water Model version 2.1 was operationalized over the continental United States, Hawaii, Puerto Rico, and US Virgin Islands. Next slide. The Office of Water Prediction's Community Advisory Committee for Water Prediction in 2019, which was the last time we met in person because of COVID, articulated some requirements for further development of the National Water Model. They requested that we emphasize improvements using observational data and identified potential sources of other data, with an emphasis on improving data assimilation techniques and processes. And they also recommend that we stand up a community development and engagement process, governance, and center to pursue proven mechanisms for community adoption. And that's what the framework we're talking about today addresses primarily. Next slide, please. The hydrologic science literature shows that models that are formulated for specific dominant local processes consistently outperform general models when appropriately applied. And this is a hypothesis known as the uniqueness of place. It also shows that models with fewer parameters that describe dominant processes outperform general models that emphasize process through parameter values. And that's the parsimony argument or hypothesis. And the real problem stems from the fact that we have a lack of a comprehensive storm flow generation theory. So there is no one model to rule them all. Next slide. The motivation for the framework comes from the fact that federal agencies struggle with model selection, identifiability, and interoperability. Legacy codes using dissimilar data models, languages, and heterogeneous computing environments impede advances. And contemporary open source software development paradigm that encourages collaboration, evidence-based selection, identifiability, and promotes interoperability offers the opportunity for us to solve some of these challenges. Next slide. The proposed solution. We've proposed development of a model-agnostic computational framework that appeals to domain scientists, uses open source software development methods, provides maximum flexibility, eases model interoperability, excuse me, allows evidence-based evaluation of different approaches, and takes advantage of each agency's considerable experience as a possible way forward. Next slide. The enabling technologies and standards come from really the intersection of computer science and engineering, geoscience data and standards, and hydrologic science and engineering. There's been a number of advancements since the National Water Model was originally proposed in 2011, some maturity in each of these areas that I think really makes now a good time to proceed with this effort. Next slide. So we're calling this the next generation water modeling, water resources modeling framework. So we often abbreviate it as next gen. We'd like it to be model agnostic so that as models, data sources, and needs change, the framework can evolve to accept those changes. We'd like a common architecture that avoids duplication and promotes interoperability. We'd like open source development that will promote code reuse and development efficiency. It'll be an authoritative repository for federal water models and ease and encourage participation by partners and the community. We'd like to apply standards where applicable for coding, coupling, data and metadata, model verification, validation, and test data. And we'd like it to be friendly to domain scientists and engineers. One of our tenets is we shouldn't have to rewrite a model to make it work in this framework. And these framework requirements are the outcomes from a joint NOAA, U.S. Army Corps of Engineers, USGS, and U.S. Bureau of Reclamation requirements workshop held a little over a year ago in October of 2020. Next slide. The framework objectives are to engage federal and academic research communities using an open source standards-based development with well-documented multi-language examples, using a model agnostic focus on interoperability, linked with NOAA and other weather and climate models, to ease scientific evaluation of coupled models and methods while running on hardware from laptops to supercomputers, with a target of 2 weeks for a domain science or engineering graduate student or new employee to add functionality to the framework. Next slide. Now, being model agnostic, the framework anticipates arbitrary model formulations. If we have a sketch or a cartoon of a real watershed with all of its land surface heterogeneity and spatial organization, there are lots of models that have been devised to try to predict the response of that system. And being an environmental prediction problem, it's firmly in the class of wicked problems. But each one of these model formulations you see here, from hill slope HRUs to tiled to structured, unstructured Voronoi, isochronous or stream tube models, conceptual models, topographic wetness index, and machine learning, they all have a place or a role to play in this problem, depending on uncertainty, knowledge of dominant processes, the importance of knowing a particular flux or state variable. Next slide. Here's an example. This is what we call the conceptual functional equivalent to the National Water Model. The little lightning bolt symbol denotes features of the CFE model that are identical to the current operational National Water Model. The little sunshine symbol denotes changes or differences from that model. In this conceptual functional equivalent model, what we did was we got rid of the 250 meter overland and shallow subsurface routing grids and the coarse resolution Richards solver, and replaced them with conceptualizations that are essentially having the same effect. So this is one example of a model formulation that is included in the current framework. Next slide. In terms of community engagement, everything that we've done is on GitHub, and you'll see that in a moment when Nels Frazier talks about the repo. We have a unification of data models that promotes code interoperability, so we can stop inventing data models. We can prevent bug reinvention by sharing code. We can support a diverse computational environment in terms of both hardware and programming languages. We can provide, there are unconstrained use cases for this framework. In fact, it might even find uses outside of hydrology. I'd say, water quality modeling might be a good candidate for that. And it provides the federal water prediction community the ability to evaluate models in a common setting. So it'll support scientific evaluation of different approaches and advance demonstrably superior approaches, which is a major advance, if you ask me, because comparing models outside of a common operating environment is a challenge. Next slide. So in terms of the collaboration, the stage is set. The agencies and our partners shown on this slide are on board with this idea of a transparent open source code development paradigm using standard geospatial data models and libraries. We selected the CSDMS basic model interface for model coupling it with some extensions to allow it to work in the HPC environment. And it meets a multi-agency need to promote science and interoperability. I would just tell community members out there in research and academia that this framework is really exciting, because if you have an idea that you believe has societal benefit, and this framework exists, you can test your idea, demonstrate its utility, and it could potentially be rapidly adopted by an agency using the framework. And with that, I'm going to turn the discussion over to Matt Williamson from the Office of Water Prediction. Matt? I don't hear Matt.
Fred, Matt is muted.
Matt is muted.
Okay.
There we go.
So apologies, folks. I think I'm supposed to be talking, but I've got a lag on the audio that's coming through, so I'm going to do my best. I've had the fortune of joining the Water Center just this past summer. So am I unmuted yet?
You are unmuted.
Okay, so we're hearing me now?
Yes.
Okay, apologies. We did a sound checkup, but I've got a weird lag happening. I'm going to do my best. Good afternoon. Thanks for having us. I'm excited to be able to present to you what we've been working on, really not just over the last 6 months since I joined the Water Center, but over the last few years in implementing some of the things that Fred talked about in this framework, really trying to. Okay, this is. I'm going to roll. So, so I'm excited to be able to do this with you guys. I want to bring your attention to the kind of Venn diagram up there, and we're going to refer back to this over time as what Fred talked about, is bringing the best of computer science, domain science, and data and geospatial science into what we're doing and how we're doing that within the next generation water resources modeling framework. So this is going to be a conceptual diagram, architecture diagram to kind of help you guys orient yourselves during the rest of the conversation. But so say we have a user that has a problem that they want to bring and they want to solve it with the next generation framework. The user is going to bring a few things. They're going to bring primarily a configuration file. Well, what does that mean? That configuration file is going to specify a few things. So it's going to specify one or more forecast models. Those may be models that are developed within the Office of Water Prediction or developed elsewhere. The user is going to specify a hydrofabric. This is a term that we're using now to describe the domain over which the forecasts will be run, including the catchments and the connections between those catchments, the ways that water flow and move within the domain. And so that's what we call the hydrofabric. And then the user will bring some forcing information. The hydrofabric and the forcing data does not have to be the same hydrofabric and forcing data that we're using within the National Water Center. It can be any hydrofabric and any forcing data, at least in theory. So once those things are set up in the configuration file, the framework will bring those in using a couple of standard methods. So one of the things that we're going to talk about a great deal during the presentation here is BMI, or the Basic Model Interface. You may have heard of this. This is used in other frameworks and other places. It came out of CSDMS and is used by a number of other frameworks. We had a presentation in our session at AGU from eWaterCycle, and they use BMI to interface between models in their framework as well. So that's how we'll bring in the forecast model code itself. BMI kind of, you can think of as defining the shape of how that model will be plugged into the next gen framework. The hydrofabric we bring in with another standard, an OGC standard called high features. So high features defines what a catchment might be and what a nexus might be. That is a connection between different places where water exists and where it will flow. That's a nexus. So we will bring that in that format, and we bring the forcing data in via any method that's supported by the framework. Currently, we're in the development stage we're in. We're using CSV data, but we are working right now on supporting more typical formats like NetCDF and other formats that we can also bring in as well. So those things will be brought into the framework and based on what's configured in the configuration file, created into what we call a formulation. So you can think of those squares within the framework as what we will call a formulation, which is a model that will run on a particular domain. Okay. Once they're in the framework will provide certain services to those formulations. For example, a time step driver. So the framework will, through the BMI interface, advance those models that are running in those formulations. It will provide, for example, units conversion between, say, the forcing data that comes in and the model that's running in the formulation, because bringing that computer science focus, we want to do good separation of concerns. We want to let the model itself do what it's supposed to do and do it best, and not have to worry about things like unit conversion or reading NetCDF files. We want to provide that capability to the model, have the model do what it does best. So it will do those things. It will read the forcing data. There are even some basic capabilities, reusable capabilities within the framework, such as an evapotranspiration calculator. And as you've noticed, those models are written in a number of different supported languages. So the framework itself will actually handle transforming the data structures that exist within those languages between each other so that those models can communicate both with each other and with the framework. And finally, once all of that is done and those models are run, those formulations are run, the final flows will be passed out to a routing module, currently TRoute, and then that will generate the final flow outputs. So that's an orientation to the architecture of the next-gen framework. And I'll hand it over to Keith to talk about some of these things, including the hydrofabric and some of the models that are being developed within OWP for use in the framework.
Thanks, Matt. First, I'd like to congratulate Dr. Tarbotton for correctly identifying our user. We've given this presentation a few times, and he's the first one to voice it out loud. If we had prizes, I'd give one away. But the first thing I'm going to talk about for this presentation is on the data science, geospatial science side of things, and that's the next-gen hydrofabric. If that's a term you're not familiar with, hydrofabric is our technical data-based representation of the hydrologic system. So in the photograph on the left, we have a stream, we've got beautiful mountains. In there, we've got some catchments, there's probably maybe a lake, a reservoir, and the hydrofabric takes those hydrologic features and turns them into a representation that's understood by the computer, as we have on the right-hand side here. And this includes catchments, flow paths that move data from one catchment to another, and nexuses between the catchments and flow paths where those data can combine into stream flow as you move throughout your stream network. For NextGen, we use a data standard called High Features, which is developed by the USGS and some other groups. And this allows us to enforce topological relationships in the NextGen system. So how we actually move data and how we run models. For now, our fundamental unit of analysis is the catchment, which is represented by this orange circle here. This is currently how we summarize forcing data. This is where we run the models. This is how we summarize parameters, output data, etc. And then once you run a model within a catchment, you can start moving data through the network via the flow paths to a nexus. And it's not always going to be the case where you have one catchment or one nexus. You're likely going to have multiple catchments. You could have a catchment flowing into that nexus, and then that moves the data throughout the system. So more catchments, more flow paths, more nexuses, so on and so forth until the end of your spatial domain. On the next slide, we have what that looks like in practice. For NextGen, we didn't want to reinvent the wheel when it comes to creating a hydrofabric release. So what we did is we started with the USGS reference hydrofabric, and then we optimized various features of it in order to better fit the next-gen system. Primarily what we did was we refactored and aggregated basins in order to optimize catchment size. So what this means, if we look at the red dash boxes here, we have a selection of areas where there's lots of little basins. And if we move over to the right-hand side, which is our refactored and aggregated next-gen hydrofabric, we see in those solid red boxes areas where the catchments have been aggregated. We did this for a few reasons. Namely, we wanted to increase computational efficiency and also homogenize our scale representation of hydrologic processes. So what this did in these two maps of the hydrofabric, we went from 281 catchments on the left to 104 on the right, and we got rid of the 177 catchments that were less than 3 kilometers squared. So on the right-hand side, the vast majority of the basins are between 3 and 10 kilometers squared. I should say before we move on to the next slide, is that we are not only working on releases of continental US hydrofabrics currently, but the tools that we use to develop these hydrofabrics are all open source, and they're available via the OWP GitHub page. So if you want to start creating your own hydrofabrics, summarize the spatial data for your models, you can do all of those via the tools that we have available currently. Now on the next slide, we'll move over to the hydrologic science side of things. So as Fred and Matt have introduced, we're using a term called formulations for NextGen. Now, a formulation can be an individual model or a collection of models and modules that represent the hydrologic balance within a given basin. And that hydrologic balance or water cycle is shown in a simplified version in the plot here. In NextGen, what the model engine or the framework does is it first ingests the forcing data. And these data are then read in and passed to the formulations. So not only is NextGen a model framework, but in our work, we've also developed and implemented a set of models and modules so that you can essentially run it off the shelf. And those include so far NOAA OWP modular, which we currently use to handle surface energy and water fluxes. This includes evaporation, transpiration, snow accumulation, and melt. And then below that in the conceptual hydrologic cycle, we have top model and CFE, which we've also implemented so far. Top model being a foundational rainfall runoff model, many of you are probably familiar with. And then there's also the conceptual functional equivalent model, as Fred introduced, and this has runoff routines designed to mimic the current national water model in a more computationally efficient and hydrologically defensible manner. We've also so far implemented the long short-term memory machine learning model, and this is done to predict basin scale discharge using a machine learning framework. Now, although these are the models and modules we've implemented so far, the formulations in NextGen aren't just limited to this list. So we can bring or we can build our own model to meet our specific needs for a given basin, for a given experiment, for a given operational purpose. Really, the only rule so far is that it has to be written in C, C++, Fortran, or Python. So we can run different models developed independently just as long as they're written in one of these languages. And the reason for that for language set currently is that we use, as previously introduced, the basic model interface for several different purposes. But one of those is to pass data from one model or module in a formulation to another. So in this conceptual picture right here, we have NOAA OWP modular passing the water fluxes to the CFE conceptual functional equivalent model. And Matt will explain more about how we use BMI in the formulations to pass data.
Thank you, Keith, who is still talking on my computer if you can hear him. So this is a little interesting. So picking up from there, I want to talk a little bit about these BMI models that are across the top. So as I mentioned, you can think of the basic model interface as being the shape that a model fits into our framework with, or maybe the pins in a socket in an electrical connector that you would use. So everything that we do with the model within the framework, we do via BMI. So we will set the input parameters using a BMI call. We will read the output values that are produced by the model and even increment the model time step, advance the model's time step rather, via a BMI call. So that opens up some very interesting possibilities for us, and we do some things I'll talk about here in a second. But returning to that configuration file for a minute, when the user defines a configuration file, that will actually have not just one configuration, but multiple configurations, because we had that requirement to be able to do heterogeneous modeling of the entire United States. So we can have different configurations for different catchments. So one of those configurations within the configuration file will bring together, say, one model, let's say LSTM. And it'll say, I want to run the LSTM model on this catchment, catchment by ID. And then I want to use this forcing data. Nels will show us this in detail in a moment. So again, the framework will bring that down and create a formulation that the framework will talk to with BMI to then model that catchment. The other thing that we can do, however, is bring multiple models, and we do this, and you'll see it in a minute. We take an implementation of NOAA MP, which we now call our internal implementation NOAA OWP, which is written in Fortran, and we pair that with CFE, and one feeds the other, and both of those models are used to model a single catchment. So we call that a multi-BMI formulation. And again, the framework handles the communication between the framework and those models, and even does things like unit conversions, and in the future, say, grid discretization conversions between the framework and models, between those models and each other, if need be. So we can really do some modular things and do some interesting and very useful things by putting together best of breed models that have different processes modeled well within them. So the framework will accomplish that, what it's doing via a couple of mechanisms. We kind of talked about the hydrofabric. So The hydrofabric is represented in high features in a geospatial format. So right now we're reading GeoJSON files that define our hydrofabric. So the framework will use that ID from the configuration, say, okay, here is the spatial domain that we're going to model, and any attributes, any metadata that's associated with that spatial domain. It will have the drivers to read the forcing data from whatever forcing data is specified. So it'll handle that, again, letting the model do what it's best at rather than worrying about how to read a particular NetCDF format. And then the models themselves are brought into the framework via dynamic linking. That is, LSTM, NOAA, CFE in this picture are compiled into DLLs or SO files or Fortran modules, and then those are brought into the executing next-gen framework. So what that means is, rather than the way a lot of models that run with different pieces, or modeling frameworks that run with different pieces in different languages do, which is run this executable and we'll dump its output to a file, and then the next thing will come along, read that stuff, and then execute based on that as input. While all that file IO that happens, the data just gets thrown away at the end, wasteful. So we are actually passing the information that's necessary between those models and to the framework in memory via those BMI calls. So that hopefully will really pay us some dividends in performance once we get to operationalization of this. So from here, I'm going to hand it over to Nels in a minute to actually go through doing this, but take from this slide that a formulation is a combination of one or more models defined to run on a particular catchment with some forcing data. And then I'll hand it over to Nels and he can show us how that actually happens within the framework. Nels.
Nels, you're speaking, but we can't hear you. Still have no sound from you.
I don't know if you're using the app or the web interface through your browser, but I would suggest using the browser interface if you're not using that now. While Nels is getting spun up, I'll just talk about this. This is the GitHub repo where the work that we've done to date lives. Excellent. He must have dropped off. He's going to try logging back in again. There he is.
Now.
Yes.
Okay. Something went weird when I shared my screen, I think. We're going to try this one more time.
We got you. Except we don't hear you. You're muted.
Nels, if while you're still sharing your screen, if you go to the little microphone icon in the lower left corner, there's a little arrow next to it. It'll allow you to select your microphone.
I am not.
Now we got you.
Okay, so when I switch back to the share, can you still hear me?
Yes.
Okay. That was odd. Moving on. Thanks for setting up the foundation of what I'm going to show here, which is just kind of to go through a demonstration of how we would start from the basics of the framework, the code, and get to running some experiments and seeing some outcomes. And so we start from our code repository here, this NGen repository is the framework code. It's the engine that links all of these things together, as Matt described. A few points here. There are some dependencies, but one of our primary goals was to develop this framework with as few of dependencies as necessary, and to make sure that when we did have to bring those in, that they were good open source dependencies that were easy to configure, build, and link in. So I want to start first by just covering a little bit more on this realization configuration. This really is the main input into the framework. And there's a lot of ways to set that up and use that to facilitate some modeling experiment. And so this figure on the right here shows a little bit about how that works. At the top level, we can set up a global realization configuration where we could say every part of our domain, we want to run model A, and we want it to initialize with this initial configuration and run that in a homogeneous fashion. But as we realize that, catchment 27 over here in the southeast part of the United States, might have a different dominant process, might need a different formulation to best capture its hydrologic response. We can override that and say, okay, here we really want model A and configuration A2, whereas catchment 11235 in the Midwest, we want to use model B. And our framework allows us to, simulate those, combine those flows through the flow paths, route those down here to this downstream nexus, and bring all of that information together. So that's where we need some required inputs for the hydrofabric that describes how that landscape is connected. We need information on the catchments, the nexus, and how they're topologically related. And then, of course, we have to bring in our forcing data to drive those simulations. And then just a note here that for our parallel implementation, where we can run this on multiple processors, we do need some additional pre-processing to generate a partitioning of that hydrofabric, that land surface, for our compute resources. So I'll dive in a little bit to kind of describe what happens inside this realization configuration. So here we're actually looking at a screenshot of what goes into this configuration file. This is just a JSON file where we have keys and values that describe the components that we're configuring. So one of the things you might be familiar with configuring a model is, your simulation time. What period of time do you want to simulate? How often do you want output to come out of that? And this also helps us link up those forcing data providers into the modules, the BMI formulation, so that we're getting data in at the right time period from these arbitrary sources. We also have in here information on routing. We say, hey, we want, in this experiment, we want to do channel routing. Here's how we're going to configure our routing module, and what information needs to go into that. But really the part I wanted to focus on is describing these formulations, because we've talked a lot about what those look like conceptually, what they look like, in this framework sense with BMI. But here's how we actually use those formulations. And so here we're going to look at the global realization config. So if you remember in that map figure, we said, hey, we can set up a single module over our entire domain. We can define that in this global key, and we say the formulation we want to run. In this instance is a BMI model written in C that tells the framework which language adapter it needs to use. And we point to where that file is being generated, that shared object library that Matt was talking about. We give it a location, say, here's the library to load to operate that model. And then in this global configuration, we can also set initialization. And this is both an important concept of modeling as well as the basic model interface that says every model needs to have some initial information, some initial conditions, parameters, options, and so on. And so our global configuration here, we can initialize all formulations over the landscape uniformly, or we can use this ID pattern to give some uniqueness of place along there, even within a formulation. The last part of this configuration I want to point out is this output variable. And so because we are using this framework to operate these hydrologic models on catchments, we want to take their response and put that into channels and route that flow. We need to know what variable what BMI variable in that formulation to query to aggregate those and connect those into the rest of our hydrofabric to apply our routing. So that's a part of this configuration as well. But then when we say, hey, we've got some catchment that we know operates better with a different model, or we think it will operate better with a different model, we can, in the same configuration file, define what that looks like. So we can say, hey, here's catchments that we explicitly want to operate different. In this case, we're looking at catchment 27, saying, hey, I want to use this, this Python BMI module to simulate this catchment. And I want this to be the LSTM module that's going to run that machine learning model. And we can also go as far as say, in this experiment, in this scenario, I want to force this with a different forcing product, a different forcing inputs that maybe are specific to the needs of this module, or for whatever reason we might do that. We have the flexibility of going very granular and making very specific changes. So here I've compiled a short video to kind of show some of these steps in action, and we're starting here. Assuming we've downloaded the code, we're going to build this. We're using common kind of industry standard tools like CMake for build configuration, make, and some other components. In this example, we're configuring to use MPI to do a parallel run. We're setting it up to use a BMIC library adapter. So we get the configuration, we get the build made. We're actually building the executable, and you'll see at the end of this, we get also a set of unit tests. And so we've included in our development a Google test suite for our code base. We compile unit tests for all of the various components that go into our framework, like forcing providers and our different adapters and so on. So we can run these unit tests to get a good sense that things are working the way we expect as we build that code. And then we can actually run an experiment here. We have some already derived hydrofabric. We've got catchment, nexus data, and our realization config, and we're going to run this on 4 processors and see it in action. And so it initializes, sets the formulation for each catchment, and then you see it start running those discretized chunks in parallel, running about 720 time steps in this example. And when it's done, we have then 2 different sets of outputs, one for each catchment in our domain, and then one for each nexus where those catchments come together, and we have aggregated those flows, and we're able to then pass those on to our routing. So doing all of that, gives us leads us to these outcomes that I want to walk through here for a few minutes. So in the last year, we've built up a lot of this capability to set out and say, okay, can we achieve the goals that we set out to achieve? So in this first example here, we're going to look at the sort of minimum requirement that we have. We need multi-language support. So we've got NOAA OWP and Fortran, we've got CFE and C code, and we need to be able to run reasonably sized domains to get to our continental goal in the long term. So here we've got HUC 01, it's about 14,600 catchments in this refactored hydrofabric, and it's roughly about 4% of CONUS. And so we can see here, running this formulation through the framework for 3 years takes about 2 hours, running on a single, somewhat large compute node with 48 cores, 96 processors. So what we're seeing on the right here is that routed response. We've done all the rainfall runoff modeling. We've aggregated those flows at the nexuses, and then routed them through a Muskingum-Coons routing, and we're seeing that response over time here. But to really show the utility behind what we did, we said, okay, that's great. We can run this model, but we need to test other models, other formulations, other ideas. So in really just a few minutes time, we can take that same setup, the same hydrofabric, and say, okay, instead of running NOAA OWP and CFE for my model formulation, I want to simulate that whole domain using machine learning model. In this case, we used the LSTM module that Keith talked about a little bit. Over the same domain, Within a few minutes, we change the realization config, point it to this new formulation module, and we're up and running. And you'll see here that, yeah, it takes a little bit longer to run this through Python, and there are various reasons that might exist, but we're still seeing, a 3-year simulation on 4% of CONUS in, 2 hours and 40 minutes. And seeing a response that we might expect from that kind of simulation. And finally, all of this leads to our ultimate goal of heterogenetic modeling. We have this idea of a mosaic where the uniqueness of place tells us which formulation to use where. And so we could do that. A little bit of extra work to define what that mosaic looks like. In this experiment, it was randomly generated, but you can see in this map in the middle where we've chosen certain parts of the domain to run the CFE and NOAA OWP model, and other parts to run the LSTM model. So technically what we've accomplished here is bringing together, modules in Fortran, modules in C code, modules in Python, putting them into an integrated runtime environment, running, 4% of CONUS on a domain for 3 years in 3 hours. And we're seeing that response from the routing again on the right. So I think this shows that we can demonstrate the capability that we set out to, and that we are unlocking these possibilities and being able to gain new outcomes with less amount of work up front. And so with that, I'll hand this back to Keith for a few minutes to discuss a little bit more outcome that we've generated from this work.
Thanks, Nels. On the slide we've got coming up here, we're going to talk about calibration. So running a hydrologic model, getting it set up. In NextGen, even running a heterogeneous set of formulations, as Nels just demonstrated, is relatively straightforward. But as we know, sometimes getting the model set up and run, that's really where your work starts, because then you need to calibrate the models. You want them to best match observations so that you can make the best, most accurate hydrologic predictions as possible. So this example calibration set I have shown here is just stream flow, as we're all familiar with, over time using a selection of different runs from a calibration exercise we performed with NextGen. But doing this, we sort of fell back into the finding calibration scripts, running it, doing the models over and over again based on parameter sets, changing them. And then we realized there is a better way we can do this. So what we're working on now is moving away from script-based calibration, which may be specific to a model or set of models, or even a specific point in time or a version of a model, to doing model agnostic calibration with NextGen. So no longer would you have to rely on a unique script for whatever experiment you're performing, but you can do the calibration using the NextGen model engine. The way we're doing that is we're extending the basic model interface to not just include input and output variables, but also to include calibratable parameters and also model option values. So you can do calibration on the fly. It doesn't matter if you have one model, if you have 2 modules, whatever your formulation happens to be, you can perform your calibration in the same manner. So that doesn't change. So you can do more efficient calibration using this functionality that we're developing for NextGen. And again, that goal is to get to more efficient, quicker, and better hydrologic prediction. And then the last slide that I've got for myself here, if you're a curious hydrologist, streamflow might not be the only variable you're interested in. And with all these model options, it can start to get complicated pretty quick as to how you're going to get output data. Do you need an output script for each one of the models or modules that you have in NextGen? No, the short answer is no, because the model engine can do that for you. As long as your variables are entered in the basic model interface as an output variable, NextGen can output the data for you automatically within the basins in which you're running NextGen. So this example here, it's from a simple run we performed in upstate New York, a few different basins running on the NextGen system, and we're showing the example output in the plot to the right for that basin that's also in the right-hand side of that map there. So here we looked at NOAA OWP modular. We ran it for a few years, and the output data we got were surface water flux, evapotranspiration in the upper right, snow water equivalent or SWE in the lower left, and ground temperature in the lower right. But if you're running OWP modular or CFE or top model or LSTM, you're not just limited to those variables. You can have essentially whatever output variables you desire, and NextGen will do that automatically for you. So you can really explore the full treatment of the hydrologic balance, regardless of which model or module you've implemented. And with that, Matt will talk a little bit about performance computational in NextGen, and before a few closing slides from us.
Yeah, just before we leave all the graphs, brief mention that we did some testing on our in development framework to make sure that it will execute efficiently when we start running it over hundreds and hundreds of processors. Initial indications, even at this early stage, are that it does that with a plum, that we've got pretty good scalability and looking forward to being able to test that. But as our target is an operational setting, we really want to make sure that happens. And so far, we're only parallelizing with processes, not even using multi-threading yet. So there's further gains to be had here. So very interesting, exciting to see. And just to kind of wrap up, so it's been very interesting getting to where we are today and looking at just what we're able to do now. So again, in that model response animation on the left, you're seeing a C model and a Fortran model passing data to each other within a process. Within a process running over a large scale scalably. And on that right side, you're seeing a completely different system, a Python model, which is machine learning and not physics-based at all, running over the same area. And then in the middle, we can actually combine those two things, have a physics-based model with two different languages combined in some areas with a Python machine learning based model in running in other areas, routing the flow between them and having them all work together to generate a single product. And as soon as we figure out how, we're going to apply those different approaches. We're going to be able to apply those different approaches in whatever areas they work best, which is very exciting. So we've got a highly modular, highly flexible framework that is built in an open source fashion. It's out there using open standards. We have really gone down the road of fixing this heterogeneous problem, both spatially and with different languages. Incidentally, that routing module that happens at the end is written in Python as well. So it's another thing in the stack. And we're working effectively and efficiently. So running 4% of the CONUS in about 2 hours in that first run. So you do the back of the napkin math and you figure we can do a CONUS in about a year per day, or about a year per hour if we scale that to 25 nodes. All this with a multi-language framework, accommodating machine learning and new technology as it comes available in a maintainable and sustainable way. That is the NextGen framework. With that, I will hand it over to Chris Massey to kind of talk about the collaboration that we're having with them on this framework and with the National Water Center. Might have had one slide. I'm leading the target, but yeah, there's a question that's been asked there several times, or at least once, about one of the links. So all of this is available on GitHub. One of those there is the hydrofabric, which has the tools that we're using to generate the hydrofabric. So that's there, and all those other things. We are getting some community engagement and collaboration that we need, and we're looking forward to having to move ourselves forward. So I'd encourage everyone here to get out there, have a look, ask questions, submit bugs, submit improvements if you're able to do so. We are looking forward to having that opportunity of working with you. Yeah, now I'll hand it over to Chris Massey, sorry.
Hey, thanks, Matt. Everybody hear me okay? Can I get a mic check? All right, great. Thanks, Fred. So yeah, I appreciate the opportunity to talk today, and it's been really great work and great presentation up to this point. And adding to that, really, we've had a great collaboration with NOAA between the Army Corps of Engineers and NOAA, as well as USGS and really multi-agency. So this idea of community-based and open source is really alive and well, and it's really multi-agency as well and with academia. So we could go ahead and go to my next slide. Yep, there we go. I think I just have one. So I really wanted to talk about how the next gen model fits in with the Army Corps' needs and uses. And to do that, we have an effort underway we're basically calling the Comprehensive Hydroterrestrial Risk Management. It's a framework of numerical models and observational data and delivery mechanisms that really help provide advanced, quantitative, actionable flood risk information to support operations within the Army Corps of Engineers. Contingency responses, planning, design, and O&M. So, for when it comes to water, the Army Corps, we've got missions that have to do with navigation, keeping the navigable waterways open to help with the commerce and so forth. Flood risk management from both the inland and the coastal side. So providing levels of protection and risk management to that. And then also with engineering with nature concept, where we're looking at natural and nature-based features, improving habitats, recreating habitats, and a lot of times in an effort for flood risk management for that. And the Corps operates both within the United States, CONUS as well as OCONUS. We have military missions as well. So one of the reasons for partnering and looking specifically at the next gen model here is that it really fits in with the framework of what we're doing, which is community-based, multi-model, multiple workflow, configurable workflows. I think the team here was just referring to those as formulations, so the same kind of thing. And allowing us to work directly with our sister agencies to speed up the overall development and accuracy of these, and to reduce the financial burdens of developing models, so that we're not developing competing technologies, if you will. So being good stewards of our tax dollars. So from the Corps' perspective, within those missions I described earlier, we really have both inland and coastal damage increases in the last few years, right? We've seen that with some of the really large storms, and with more people being at the coast, more infrastructure at the coast, as well over the last 40 years or so. And flood risk assessment is oftentimes reactive and for us, and lacks critical hydroterrestrial system context, whether these be some of the dam operations or things like that. Floodgates and so forth. And so being for the Corps having to operate some of these flood structures, accurate assessments of rainfall runoff and river flows coming in from the National Water Model are critical for that within the United States. And then being able to take these same models and create our own catchments and setups that we use around the world for our military and partner agencies overseas. And then when we consider these in the context of rising sea levels, and as we know, we've got a lot of aging infrastructure, these are really pointing to some critical needs where having these very accurate models and capabilities with flexibility, where we're able to build complex workflows and put in the best models for the best areas without having to reinvent the wheel each and every time. So for that, we're looking at common operating frameworks ourselves, within looking all of the models that we particularly use oftentimes for design features as well as operations, and being able to use those in this common framework as in the next gen National Water Model here that we saw as well. And so needing, for us, the need to be able to assimilate observations as well. I believe this framework that we presented here certainly has the capabilities of bringing in observational data for assimilation in there to improve the forecast as well. And again, just reiterating the strength of this modular numerical methods and physics-based packages, and the ability to link models to build these complex workflows or formulations, as we were calling them a while ago. And then, as we saw the demo in terms of verification validation within the same model, looking at uncertainty quantification, right? So we have a certain amount of uncertainty in our system, and we run that through the models. How does that uncertainty propagate through? And use of those for error terms and the need for accuracies of input data, for example. And for us, really, looking at these is a reduction in flood risk and casualties in particular due to disasters. And of course, NOAA's got the forecasting mission in the United States for that. But in terms of infrastructure, the Army Corps are the ones that are designing and building and operating these as well. Reduce time and cost, improve skill. So leveraging the same kind of ideas and using the National Water Model and these next gen concepts are very much in line with what we're trying to do here. And come back full circle again, really just working with our federal partners here just does a world of good in terms of strengthening the overall products that are being used and the development of new capabilities and technologies and moving forward with some of the best forecasting and model data that's out there. So I appreciate the opportunity to speak today and look forward to continuing our partnership with NOAA and the other agencies as well as academia. So I'm going to pass it back to you, Trey Flowers, I believe.
Indeed, that is correct. Thank you very much, Chris. And I do want to thank everybody for their contributions today, for Tom for talking about the strategic underpinning for why we have been moving in this next generation framework development direction. For Fred talking about the process that we went through with the requirements, Matt, Keith, and Nels for their walkthrough of the demo and showing us that one of those major underpinnings that we've been trying to achieve, that truly heterogeneous hydrologic modeling approach at large scale that enables the domain science, the multilingual approach, that graduate student test that Fred was talking about, that really is possible for us as a viable approach for us going forward. And by us, I mean the community at large. And then finally, for Chris for giving us the perspective on where we can go and where we can partner as a community, and giving us the federal perspective on that. And so we have plenty of time available for Q&A. We have the line until 2 p.m. Central, and we will try to answer as many questions as possible. So I would ask for everybody to please put your questions into the Q&A function for Zoom. I'm not sure that everybody can see them if they are entered into the chat. So we'll try to get through. There have been one or two that have been asked during the call. I'll go through the answers to those really quick since they have been answered already, just to make sure that everybody hears them. The first was, will the slides be shared and will the recording be shared? The recording will be up on Kawazi's YouTube later today. And I believe Julia has entered the YouTube channel, the website for that, into the chat. The next question came up, is NextGen distributed by catchments rather than the current grid based on square kilometers, e.g. for forcing and parameters? So Keith typed a message into the Q&A. I'll read his answer and then we'll open it up to the panelists to see if anybody wants to add to Keith's answer. So Keith said the NextGen framework currently uses catchment discretizations for models, forcing data, parameters, etc. We're developing functionality for gridded models running on NextGen and passing data from a grid to a basin. So yeah, Keith is right here. The the whole goal of this framework that we're developing is not to limit the ability of the domain scientists to model in the way that is most appropriate. So if a gridded formulation is most appropriate, then we want to have the flexibility for the domain scientists to be able to model using a gridded formulation. If catchment makes more sense, then we should have that flexibility as well. Fred, Keith, Nels, Matt, anybody want to add to that response?
I'll just chime in quickly. Trey, thanks. Say it's model agnostic. If your model needs a discretization to do an area, you apply that discretization, and the model manages what's happening within that part of the domain. It's a complex coupling problem when you start talking about models that have to communicate across watershed boundaries, et cetera, and we haven't solved that, but we've identified it as an important coupling problem that we have to deal with.
All right, thank you very much, Fred. And then the last question that was answered during the live session was from Kevin. Can we share the GitHub link for the code that allows users to build their own hydrofabric inputs? And we did share that link, and I believe Lauren dropped all the links for the OWP Next Gen information into all of our GitHub repositories into the chat. So we'll move on to the open questions. The first one is from John Lotek. And this is open to anybody on the panel. Is there an undying database, or is it just file IO and calculations in memory? Maybe Nels or Matt. I'm not sure if we're still dealing with Matt's lag issue. Maybe Nels or Matt, you want to take that one?
Yeah, I can start with that. Currently, there is not, and I'm guessing that's underlying database. An undying database scares me because I don't want zombie databases. Forgive the humor there, but no, there is not a unified database at the moment. But the intention and the design behind this framework is to be able to pivot to that. If that becomes a need of the community, a need of our operations, a significant need, we can interface a database into the system if we need to. And we're building up the components of the framework with abstractions in place to allow us to source data from a database or from NetCDF files or from CSV files and deal with those in a modular way so that we could support any of those types of inputs or outputs that we need to.
Thank you very much, Nels. The next question we have is from Trent. So the vibe I'm getting is that river forecast centers will benefit from computer science, data science, hydrologists if they want to utilize the Next Gen framework. I'm looking for a route to recruit the people we need to use these models. The partnership with Quasi would be great to get projects based on RFC needs funded with supportive engineering faculty. Ohio River Forecast Center has ideas, and we're happy to work with anyone. Thank you very much, Trent. I think the academic community at large and as well as the federal family are happy to work with you as well. I'll open that up to the panel. Tom, Fred, anyone else want to add or respond to Trent here?
I'd like to add, Trent, that's a really good point. I think it's one of the exciting things about the framework. As a former professor myself, your model comes with, all models come with a data model and peculiarities around their use that the framework, by using standards for coupling and data, just dispenses with those. So it makes compliant models that use the BMI standard and that understand the underlying hydrofabric. It makes using them almost plug and play. It's not that simple, but it's a lot simpler than taking a brand X model, trying to understand all of its nuances, work around its differences and all that. So that's a really good point. I think it's an exciting recruiting point to make when you're trying to get people on board as well.
Very well said, Fred. All right, our next question comes in from Albert. How long would it take a user with no experience with the framework, but a good foundation of hydrology and programming to get the model up and running on an example watershed? Have any tests been done on personal computing machines for education as an alternative to SWAT, VIC, et cetera? Fred, do you want to take that one maybe to start?
Sure, I can give you an example. One of our team members who's a GIS specialist with a lot of understanding in computer science was tasked with getting top model converted to run in the framework. And I'm thinking about Jessica, and that took her about 3 to 4 weeks, as I recall. And that's I think a one data point sample that just shows the challenge in the amount of time. It isn't the 2 week that we've gotten our target, but she had to learn. She didn't know anything about BMI either.
Yeah, that's a great point. That 2 week target is something that we are working towards. We're not quite there yet, but that is absolutely the goal, is to make it as approachable to domain scientists, to students as possible. There was a second part of that question. Have we done any smaller experiments as an alternative to SWAT or VIC?
Yeah, we've incorporated the Shannon-Jane runoff scheme from VIC into the conceptual functional equivalent model, and we're testing that. But we haven't done anything with SWAT yet.
All right, thank you, Fred. Our next 3 questions are all from the same person, so I'll take one, and then we'll get to the others, time permitting. So this question's from James. Truly awesome work and very exciting. This question is more for Chris. Chris, the Army Corps of Engineers has a lot of code that could be part of these tools: impact assessment, river routing, reservoir management, et cetera. Is there a path for those to be made part of this open ecosystem?
Yeah, that's a great question. And I can say there's an overall effort within the Corps to move toward open access tools and open source whenever possible. So there are efforts underway to get these tools so that they can be included in a system like this, or others with that. It doesn't necessarily mean that some of these, the legacies codes would be changed overnight, but the overall effort within the Corps is to move to open source, open access tools. So I would say yes.
All right, thank you very much, Chris. And the next question is also mentions your name. So this is from Steve, and then we'll go back to some of James' other questions. So Steve's question is, there is reference to federal agency collaboration, slide 18 in Chris Massey's slides. What is the plan to engage the private sector to participate in the open source paradigm and contribute to the next gen framework or national water model advances? So anyone want to take that one?
So Trey, I'll chime in and just say some of the efforts the Corps is undertaking. So I know the Corps and NOAA and USGS and others, as well as a large group of academia, are part of this coastal coupling community of practice, where we have a large group of academia and private sector folks involved in that. And the event, it certainly overlaps and overlays with the national water model and this next gen paradigms and the open access pieces of that. I think also from the presentations today, as you've seen, we've got these GitHubs that NOAA is posting their work on, where you can download and go from that, and certainly would be able to contribute back to those. And in the same vein, the Army Corps, with a lot of their tools that are already open source, there are many on GitHub and other sources like that as well. So I think, just through conferences and presentations like this, getting the word out that these agencies and so forth have these open source tools and are accepting and willing and want private sector as well as academia support to come back in with these. I think it just really adds to and solidifies the idea of community based, right? I don't think NOAA, the group here, or the Army Corps, when we talk about community, we don't just mean federal community, we mean the community of practice. So this would be the entire group there. So those were my thoughts on that.
Thank you very much, Chris. And I'll echo that, the community word that you mentioned in your response. My response is we are building a community, not a club. We're working in this next generation framework to make it enables the science that we need to do to advance water prediction. We're making this tool available for anybody to be able to use and hopefully contribute to, both from the framework as well as the domain science side. Will there be funding available for the private sector? That remains to be seen. It is something that is a possibility in the future. There are no definitive plans on that as we sit here now. So yes, we do encourage the private sector to work with these tools, to develop these tools, to engage with us as a community. We need contributions from all members of the community, the federal family, the academic community, the private sector. All are welcome, and contributions from all are encouraged. So great question, Steve. Let's go on to another question. Maybe we'll take Jude's, and then we'll go back to another one of James' questions. So can someone, maybe Keith, please elaborate on the calibration results, general accuracy, geospatial tendencies, etc. Mainly, how well does it work? Where does it work well, and where does it work not so well? So Keith, maybe you want to take that, and then I can add some additional information. Maybe Fred has something that he wants to add as well.
Yeah, I'll give, I think, the short version, and then Fred can follow up with whatever pieces I perhaps missed. So Jude, one of the things with NextGen is that it allows you to choose the model or model sets that work best wherever you run. The framework itself does not necessarily mind which model performs better than another model in a different location at a different point in time. Some of the things that we're actively working on for NextGen is the evaluation phase. So we know from, as Fred illustrated earlier with the point that there's no one model to rule them all. We know after years of hydrologic research and myriad hydrologic model intercomparisons that we're just never going to get to the point of making perfectly accurate hydrologic predictions over large spatial scale, particularly in an area that's as hydroclimatically and physiographically diverse as the United States. So what we're trying to do is take that next step, and as Nels and Matt demonstrated with the heterogeneous formulations, where we can actually assign the best model or model sets to basins. And so the which model isn't necessarily that important. It's just that it performs better than the others, and we can get the correct answers, and the correct answers for the right reasons.
Yeah, that's good, Keith, and that's the hope, being model agnostic and allowing intercomparison is the real strength of the framework. We envision a calibration evaluation cycle, but we're even going to let users choose what calibration routines they use. So it's really non-specific and allows kind of open-ended scientific evaluation.
All right, thank you very much, Fred. And that one of the things we're planning. So Nels, if you want to advance one slide, maybe the last question in this question can we do have 2 more slides. So one that gets the last question about the private sector. Our GitHub repo, here are the links to the GitHub repo. Our next gen where the framework lives, our strategic plan, which Tom spoke to in the beginning, our Twitter account and our YouTube account. So we are certainly interested in engaging with the community across all sectors. Here's how to connect with the Office of Water Predictions. All of the presentations that we made at the AGU fall meeting, which just happened last month, are in the on a GitHub repository, so you can go see what we're doing, and hopefully come and contribute to that. And speaking of that, there is a next opportunity. Nels, if you'd advance one more slide. So there's a new AGU conference coming up in June. Abstracts are due next Wednesday. We will be sponsoring a session along with our partners at the Army Corps of Engineers, COASI, as well as the National Ocean Service. We have a session, it's 142579, and it's centered around this theme of advancing water resources modeling through developments in domain, computer, as well as data sciences. So if anybody out there is interested in the next major touch point with us for discussion of these ideas, we'd dearly love to see you at Frontiers coming up in just a few short months. And so that's my answer to that. Great question, Jude. Thank you for asking it. All right, our next question is again from James. What are the next steps to allow the community to make meaningful contributions? Excuse me. What are some of the lowest hanging fruit? This is multiple questions in one, but we'll try to get through them. Essentially, what are the next steps for engaging the community? So, other than the ones I just outlined.
Yeah,
I
so
can
Trey, I have a,
Go ahead.
go ahead. So I have engineered a workaround for my audio problem-ish, and I'm telling myself to go ahead, so it's not perfect. So part of the answer to that is wherever you want to get involved. So there's a lot going on in that GitHub repo. We are, trying to figure out how to move more of our process out there that is putting things we need done in as issues that people can come and pick up. So look forward to that over the near future. A lot of repos actually have help wanted tags on their issues, and I think we want to try and do that if we can. It is a pretty early state right now, so it does take, as Fred was suggesting, a little bit longer than we'd like to get started and get rolling, but it is possible, and get with us and we'd be happy to help you do that. Yeah, anybody else?
So I'll provide a little bit of additional detail here. So the Frontiers meeting that we have. So our initial demonstration of this at the fall meeting last month was to show that a heterogeneous multilingual hydrologic model running at a maybe not a continental scale, but running at a reasonable scale was achievable. The goal for us in the Frontiers in Hydrology meeting is to produce a more of a demonstration of a complete hydrologic modeling capability. We don't have all the bells and whistles turned on in the demonstration that we have right now. So we're going to be exploring some of the snow. We're going to be exploring some of the soil moisture, frozen soils, routing, and incorporating the data assimilation scheme we use in the existing national water model, reservoir routing. Some of those types of things are what we're going to be aiming for. We may not be able to achieve those, but we're hoping that we can show that by a heterogeneous model permutation that we'll be able to show an increase in skill over a homogeneous permutation. So that is, we're not sure that we're going to get there, but we're very much aiming for that target by Frontiers. So in terms of where we're going next, it's more adding sophistication and scale to what we have. It's bringing the people from the community in. We have a few complete model formulations. It would be great to see other formulations being contributed by the community. We have a few individual modules, which are the pieces that compose formulations. It would be great to see the community contributing those or working on those. We're doing everything that in the complete open source. You can follow along with the links that Lauren has dropped in the chat. You can follow along our progress there and hopefully begin to contribute. So we do have a couple of questions that were answered. We do have one from Seth that was put into the chat. I'll go ahead and ask that one live. So the open source, he starts off with a compliment, really likes the approach. So he's wondering if the models are discretized, what impacts on operational forecasting will be seen in terms of simulation order and timing and basin to basin transfer? So Fred, maybe you can take that one.
Yeah, sure. I did type an answer into the text, but I'm going to recap what I said. We don't want to solve everybody's problems. There's some really interesting hydrologic prediction problems to solve. And the framework right now uses catchment-based lumped models. We envision going to tiled, semi-distributed, fully distributed. And then when you start talking about, as I mentioned earlier, if you have to pass fluxes across catchment boundaries like interbasin groundwater flow, that becomes a really complex coupling challenge. Not only do you need to know which basins are next to each other, but which elements within the models of those basins are adjacent to each other. We know how to do that, but it's not easy. So in terms of the development of the framework, our hydrofabric is catchment based, and I don't think that's going to go away. If you do want to simulate some kind of interbasin flux, that's a coupling challenge that will require a very special coupler along that boundary that we haven't developed yet. But it's in the task or the list of things that remain to be done.
Great answer, Fred. And the very much in line with the community challenges conversation that we were just having. you're absolutely right. We're not going to be able to do this all within the walls of the Office of Water Prediction. And so engaging the community and having the community to contribute solutions to their own problems is very much going to make this an energetic and interesting place to work, or space to work, over the next couple of years. One thing that I will add on to that is, in terms of the simulation order and timing, our expectation with this development is that we will see a more computationally efficient model for our own particular use, that will be able to only spend the compute necessary on the processes that we need to simulate. And so we do anticipate a model that will be as efficient or more efficient than our current modeling system. We don't have any proof of that yet. We're still very early in the development stages here, but given what we've seen so far, some of the very preliminary numbers that Nels threw out, or maybe Matt threw out, in terms of our benchmarking, that it certainly shows promise at this point. So we have the last question is also from James. In the spirit of opening this to the community, what plans are there to make the available standard configurations for testing and experimentation? And so maybe I'll take that one first. Again, we're working in the open source, standard test, or something that I believe we should be contributing to the community. So yeah, everything that we're doing is going to be made available through similar pathways. So anything that anyone else that wants to add to that? Matt, maybe I saw you came off mute.
Yeah, I could say that unit testing and automated testing of the framework itself is something that we have focused on a lot, trying to make that happen. And all of that is already in all the work that we've done in that so far is already in the repository that you'll find. And I think I'd echo what Trey said, that is, as we have validation suites, we would definitely hope to be able to make that data available, the base data and the output, such that others could reproduce our results. Yeah, we would plan to make all of that available within the repositories, I would imagine, to the extent possible. Large data sets, before AGU, we were trying to figure out, okay, how would we make large data sets available to people so that they could use them to play with or test the framework? And that's going to be a challenge, but we do definitely want to make those available.
Thank you very much, Matt.
Can I chime in just to follow up on that comment for a second, Trey?
Please do, Nels.
Some of those issues that Matt was just talking about, I think, are also ripe for our community engagement, right? Dealing with hosting and sharing large data, we do have community partners who specialize in that area, and then there might be ways for us to collaborate on those kinds of loose associations. How do we just continue moving things forward so people can work together? And so I think, yeah, we may or may not be able to solve some of those technical challenges with the way we're operating and working now, but there's a lot of room to continue to improve the leverage, existing or developing technologies in cloud computing, with shared resource management and so on. So I'm excited to see those kinds of collaborations at an engineering level start to come to fruit too.
I'd like to add to that too. The WaterML 2.0 high features data model is not complete, in that it doesn't describe groundwater catchments. It doesn't describe cross-section or a long channel topographic information, like embankments, things like that, flood walls, explicitly. There, in terms of all three of the big areas, domain science, computer science, and hydrologic science, there are big unresolved methods or questions that we need to identify methods to solve. That's another really fertile ground for collaboration with the community. And I think that as people get into looking at the standards that we've developed and see places where additions or changes are needed, feel free to suggest those. We've already gotten several people looking at the code on our repos and asking us questions or suggesting changes to the code to make it more useful for what they want to do. So we've seen the beginning of community involvement in our repo since AGU, and I hope that accelerates.
Absolutely. Well said, Fred. All right, I believe we have gone through all the questions that we had, and we can transition into the wrap up. So I think Julia, you'll want to wrap us up from the Quasi side, but I'd like to say a sincere thank you for everybody. This was a great discussion, in my opinion. Our speakers, Tom and Fred, Nels, Matt, Keith, Chris, very, very much appreciated. We're excited here to be present at the creation of this system, to be at the founding of a new community. The pioneers of doing something that we've all acknowledged has been a good idea for quite some time, and it's never gotten off of the ground. And we believe that we're going to get off the ground now. And so want to thank you for your attention today. Fred, do you want the last word from the OWP side?
I just want to thank people for attending and listening. I appreciate the questions. We really are excited about engaging with the community. And as one of my last slides said, I think the stage is set. If you believe that you can help to advance water prediction, not only within the United States, but in general, the framework is available for you to adapt your models to work with it. And we can get out of the business of reinventing data models. We can take advantage of standard data sets and forcing data sets that the framework is aware of, and start to advance the science in more than an incremental way that depends on, all of those things that determine who wants to use a model and who doesn't. When we teach students to use a framework like this, all of a sudden we're opening up what you might call an ecosystem, and it will amplify all of our efforts together and allow us to make advances in hydrologic prediction that have been evasive in my entire career. So with that, I'd like to say thanks to all the participants.
All right, I'll jump in here very briefly to wrap us up. I want to reiterate a huge thanks to all of our speakers and panelists today for taking the time to share the work that they've been doing. It's been really fantastic seeing all this work come together, and excited to see where it'll go. And thank you for sharing all of this with the Quasi community. One last plug from me. If you happen to be listening or watching the recording and you're a graduate student, and a lot of the topics that were covered today are especially of interest to you, please consider looking into the Summer Institute. Applications for that are open now. It's a summer program where you get to work on projects relating to the mission of the National Water Center. And the link to that program has been included in the chat and will be included in the YouTube recording caption. Thank you all so much for your time, and have a great rest of your day. Bye.